Hello, welcome to this video which presents the challenges related to online machine learning-based early decision making. This is the issue number 5 of the 7 video series, which presents the main ideas of the founding paper of this new research field. In this video, we will open a new lock by considering a decision period that is not determined beforehand and which is of indeterminate size. Here, the input data of our system is no longer a time series of non-maximum size, but a data stream. Intuitively, a data stream can be considered as a time series of infinite length. More precisely, the beginning and the end of the stream are indeterminate. On the one hand, the beginning of the stream is considered as too old and has been forgotten, as a finite amount of memory is available. On the other hand, the end of the stream will potentially never be reached since new measurements are continuously arriving. To process such data stream, only a part of the most recent measurement is usually observed. In this example, this is the sliding window that appears in orange in this slide, which starts from the current time and goes back to the past for a certain number of time steps. Compared to standard machine learning-based early decision-making, considering a data stream has a significant impact on the use case which can be addressed. For example, it becomes possible to continuously monitor a system in order to detect anomalies as early as possible. Continuous monitoring is not possible with standard machine learning-based early decision-making because it implies to divide time into periods, for example in days. To illustrate this, let's examine what the training set looks like in both cases. In standard machine learning-based early decision-making, the training set is a collection of examples from a periodic time division. For instance, each training examples may represent 1 day of server operation. Within this day, there is a finer temporal division for which each time interval is associated with a label. By contrast, in the case of online machine learning-based early decision-making, the training history is considered as continuous, without having to divide it up according to a fixed time period. In the case of online machine learning-based early decision-making, the first obstacle is that the type of prediction to be made is complex. Indeed, at the time of triggering the decision, the model must predict online both the label of the next event and the time interval over which this event will take place. This time interval can be located either in the future or in the past. Now, let's look at what happened just before triggering a decision. In this figure, the time interval which appears in gray corresponds to a potential anomaly. Our system starts to suspect that this anomalous period is about to occur. In the case of online machine learning early decision making, the trade-off between earliness and quality of decisions is defined in a different way. As time runs out, the sliding windows get closer to the suspicious time periods for which an early decision is required. This quality versus earliness trade-off has been formalized in the particular case of early classification of events in open time series. To learn more, you can read the article which is given as a reference at the bottom of the screen. This work will be continued to address the general case of machine learning-based early decision making. As a reminder, approaches in the literature produce early decision by using two types of model. First, a collection of predictive model is used, and the triggering model is then used based on the output of the predictive models. These two kinds of models are applied online as new pieces of data arrives. However, these models have been previously learned in batch mode. These models are able to predict both the next event and its location in time. In the data stream processing literature, most of approaches are able to handle non-stationarity. Indeed, drifts in the input data can occur, that is to say, changes in the data distribution. In the case of a classification problem, these drifts are divided into three types. First, a concept drift occurs when the separating boundary to be learned changes over time. Second, the covariate shifts correspond to the case where the distribution of the input variables changes. Finally, the prior distribution of classes can also change over time. The management of these different types of drift is an interesting challenge to develop the field of machine learning-based early decision making. The research directions described in our paper fall into two categories. The first one consists in detecting this drift and then retrain the model by using recent data. Such approaches exist in the data stream literature. The challenge here will be to adapt them. The second track is more original as it consists in learning online both the classifier and the triggering model in a joint way. The challenge is to learn online these two kinds of models which are mutually dependent. Indeed, in the existing approaches, the triggering model is learned in a second time based on the output of the classifiers. Finally, this slide summarizes the three new challenges presented in this video. Challenge number 5 consists in making online predictions which are localized in time. Challenge number 6 consists in redefining the quality versus earliness trade-off in the case of online early decision making. Finally, challenge number 7 is more difficult and aims at managing non-stationarities in online early decision making. To conclude, in this video we have underlined the importance of the challenges related to the online learning. In the next video we will open the last lock and we will talk about revocable decisions. Thank you very much and see you soon!